Okay, for our second talk this morning, we have Diego Ruiz from Madrid, and the title is up there, Hitchin-Kobayashi correspondence for bundles with parabolic structure.
So thank you very much for the introduction, and thank you also very much to the organizers as well. And well, as I say here, this is based on joint work with Oscar Garcia-Prada in preparation, and it's regarding a Hitchin-Kobayashi correspondence for bundles with a parabolic structure group. So let me say just at the beginning, so not, as to avoid confusion, that what I mean by the title is that we're going to be working with bundles where the structure group of the bundle is a parabolic subgroup of a given complex and connected reductive group. So please do not be misled by the word parabolic here. And just as a brief refresher, although thanks to the courses and the speakers on the second week, we are all very well acquainted with this at this point. But let me fix a holomorphic vector bundle over a compact and Kähler manifold X. And I will be thinking about such a holomorphic vector bundle as a pair given by a smooth complex vector bundle together with an integrable Dolbeault operator. And in this setting, we have a very celebrated generalization of the very celebrated theorem of Narasimhan and Seshadri, which is the following, is the assertion that there exists a Hermitian metric solving the Hermitian-Einstein equation, this one over here, if and only if the corresponding holomorphic vector bundle is slope polystable. Of course, this was proved by Donaldson and Uhlenbeck-Yau in different stages. And we may equivalently restate this theorem as the existence of a bijection between the moduli space of Hermitian-Yang-Mills connections in this Hermitian vector bundle and the moduli space of polystable holomorphic vector bundles whose underlying smooth bundle is given by E. And in either formulation, this is known as the Hitchin-Kobayashi correspondence. So ever since this seminal result appeared, there has been various analogs and generalizations, in particular to principal bundles. For example, Ramanujan in 1975 gave a generalization actually of the theorem of Narasimhan and Seshadri. And also Ramanujan and Subramanian in 88 gave a generalization of this theorem to principal bundles with a reductive structure group. And there are, again, more general situations for bundles with extra structures, for families of bundles. I want to highlight here some contributions which are very general Hitchin-Kobayashi correspondences which attempt to encompass many of the particular instances in the literature in a single framework. For example, the one by Banfield in 2000, Mundetti-Riera in 2000, a refinement of the previous one by Steve Bradlow, Oscar Garcia-Prada, Mundetti-Riera, Lubke Telemann, again, Garcia-Prada, Goten, and Mundetti-Riera.
Ask a question.
Yes.
I'm just confused by the order. Some date wrong because it says this was generalized by Ramanujan.
Yeah.
The date of the Ramanujan theorem is 10 years before.
Yeah, because actually this when X has the complex dimension 1, this is the theorem of Narasimhan and Seshadri, which came a lot before. So Ramanujan actually generalized the theorem of Narasimhan and Seshadri. Yeah.
60s or something.
Yeah. Well, in all of these correspondences, at least on the nose, an important point is the fact that all the bundles which are involved have a reductive structure group, at least on the nose. So a natural question comes up is, what if the structure group is non-reductive? For example, what if it's a parabolic subgroup of a given complex connected reductive group? And of course, there are many things that could go wrong and do go wrong if you try to do this. But there are some very general arguments that seem to suggest that such a thing might be possible. But instead of telling you that, which I will briefly comment later on, I'm going to give you something better. I'm going to give you an explicit example where this is achieved. So let us consider extensions of vector bundles, which are short exact sequences of holomorphic vector bundles, such as this, I will assume, over a compact and Kähler manifold. And this is equivalent to giving a holomorphic P bundle, where P is a maximal parabolic subgroup of GLNC, given by this block upper triangular matrices. So this part here, the off-diagonal term, accounts for the unipotent part, and the block diagonal part is the Levy subgroup, the maximal reductive subgroup. And we can realize that these two things are the same by taking the frame bundle of this bundle in the middle and realizing that because it has this holomorphic subbundle, its structure group reduces to P. So let's try to run the same program as before. First, we need to understand holomorphic structures in terms of del bar operators, for example, so as to relate them to connections. And a natural way to do this is to choose a del bar operator here such that upon a restriction to E1 and projection to E2 gives me del bar operators on E1 and E2, which is exactly what I said here. If you do that this extension at the smooth level splits, not at the holomorphic level, but at the smooth level it does. So if you use that, you can write this del bar operator in this matrix form. You have these diagonal terms account for the del bar operators, and this 0 here accounts for the fact that E1 is a holomorphic subbundle. And then we have an off-diagonal term, which is a 0-1 form with values in these homomorphisms from E2 to E1. And the integrability of del bar is restated in terms of this data as follows: the integrability of the induced del bar operators and this coupled condition. Once we have this, we can write down the Chern connection, which is written there on the blackboard. So we can, we have a relation between holomorphic structures and connections. Also, we would need to understand the gauge group, and in this case, is not very difficult to realize that the gauge group is given by the semi-direct product. This part over here is the gauge group of E1, the gauge group of E2, the complex gauge group, of course. And the normal subgroup is given by homomorphisms from E2 to E1. And let me state for what's to come that notice that this gauge group has a semi-direct product structure just like the structure group P itself. And if you take a look at this part, it looks very similar to what an infinite dimensional non-reductive group should look like. So keep that in mind for the future. But once we know that, we can write down some equations. So to generalize the Hermitian-Einstein equation, one natural option is to take on the left-hand side, the usual Hermitian-Einstein term for a metric on the bundle E, and deform the right-hand side so as to respect the smooth splitting. So we allow for two different constants on the right-hand side. And we may restate this equation in these equivalent formulations. This is an equation again for a metric on the bundle in the middle of the extension. This is the projection onto of E onto E1.
Sorry, Diego, just that both the unipotent and the reductive part is infinite dimensional in that case?
Here, yes.
So we know that they are both. Okay.
And well, this is an equation for such a metric. This second condition is just saying that E1 is a holomorphic subbundle. And we may even restate the equation as a system of coupled equations for a metric on E1, on E2, and the 0-1 form here, this system. So there's a moment map interpretation of these equations. Actually, for this one, the moment map is, in some sense, the natural one, what you would expect. I will comment on that later on briefly. But these two equations have a more subtle symplectic interpretation. And that was actually, to understand this, was part of the motivation of this work. And let me state also that in 1995, both Steve Bradlow and Oscar Garcia-Prada, and in a different work, Daskalopoulos, Uhlenbeck, and Wentworth, proposed some stability conditions depending on a certain parameter alpha and prove a Hitchin-Kobayashi correspondence for all of these equations, because they are equivalent, when alpha is equal to tau2 minus tau1 and it's positive. So now that we have an example, what we're going to try to do is use this example as a blueprint for the general situation. And we will actually see that this example, although it doesn't include all the subtleties, the main features are already here. So we can use this as a guiding tool. First of all, what we need to understand, the holomorphic structures. So let me choose H, a connected complex linear algebraic group over C, and a complex compact n-dimensional manifold. So far, no assumption on the metric structure, and a holomorphic H bundle over X. And we saw this last week in the course by Brian Collier, but let me remind you, for a smooth H bundle over X, an almost holomorphic structure is an almost complex structure on the total space, which makes the projection and the H action pseudo-holomorphic. Yeah, I said, yeah. So this we can say holomorphic, and so to speak, this is the differential geometry's definition of a holomorphic structure. So consider first, yeah, that this is a smooth H bundle, and this is the definition of an almost holomorphic structure. And if you erase all the terms in brackets, you get the differential geometry's, so to speak, definition of a holomorphic H bundle, which is equivalent to the usual one with transition functions. So we can take for any such EH smooth bundle a smooth L reduction of the structure group EH. This is important. This is just the smooth reduction. This happens because U is contractible. And note, moreover, that EL, this is easy to prove that EL is bundle isomorphic as an L bundle, because L is isomorphic to H mod U, to EH mod U. And hence, this allows us to prove that EH as a smooth manifold, so the total space of the bundle, is diffeomorphic to EL cross U. This essentially follows because the projection of EH onto EH mod U is a U bundle. So the choice of a reduction is a smooth global section, so it must be trivial. And as a smooth manifold, we have this. Whoops, sorry. And just with this data, we can already prove that the gauge group of the H bundle is given by a semi-direct product of the gauge group of the L reduction together with an extra part, the normal subgroup, which is basically smooth sections of this associated bundle, which is the associated bundle with generic fiber U by the adjoint action. So far we have already recovered our knowledge of the gauge group that we saw for extensions. Now let us take J, an almost holomorphic structure in such a smooth H bundle, and since EL is a bundle isomorphic as smooth bundle to EH mod U, it has an induced almost holomorphic structure, which I call a J hat. So J induces an almost holomorphic structure, J hat on EL, and we can prove actually the following classification or characterization of almost holomorphic structures here. So using this diffeomorphism, we can write every almost holomorphic structures on EH in this form, in this matrix form, where GU is a complex structure in U, J hat is just the induced almost holomorphic structure on EL, RU is just the right multiplication, and the only piece of data that we're missing is this 0-1 form in L with values in the Lie algebra of U, and this subscript means that it's right equivariant with respect to the adjoint representation and horizontal. And there's a canonical isomorphism with this space, as Brian Collier told us in his course last week. So almost holomorphic structures here are determined by two pieces of data. They induce almost holomorphic structure in the L reduction plus this 0-1 form. And moreover, if J is integrable, so the almost holomorphic structure is an honest holomorphic structure, well, this condition is equivalent to J hat being integrable and J hat and this form phi being solving this coupled Maurer-Cartan equation. So to give a little bit of a geometric interpretation of this result, you can prove from this result that this implies that J can be understood as a deformation of the product complex structure in EL cross U. The deformation is given by the 0-1 form, and this actually, for example, explains the appearance of the Maurer-Cartan equation here. So, so far we've understood holomorphic structures a little bit better, but we need to act on them by the gauge group. So the gauge group acts on holomorphic structures by conjugation as usual, but since we can write it down as a semi-direct product, this action of the gauge group induces, first of all, an action of GH on the holomorphic structures in EL, which is the one you would expect to appear, the naive one. We just project onto GL and we act by the projected gauge transformation. But it also induces, and this is the interesting part, an action of GH onto the 0-1 forms of X with values in this associated vector bundle. And it's given by this formula. This is not going to be too important for us now, but this is just what's called the logarithmic derivative of F. And well, this is the formula. Note that this extra bit adds a little bit heuristically like an additive group, so to speak, quote unquote. And to understand this formula a little bit better, well, first of all, note that we have a map between isomorphism classes of holomorphic structures on EH to isomorphism classes of holomorphic structures on EL. And then this follows from what I've said, but this is a standard fact that you can prove in many other ways. But using the theory of non-abelian cohomology by Grothendieck, you can identify the fiber of this map with this space over here. This is the one cohomology set associated to this sheaf of non-abelian groups. And this is the zero cohomology group. And what we can prove is that using a very general theory of non-abelian cohomology due to Onischik, which in particular includes Grothendieck's non-abelian cohomology, we can recover this result from the previous two propositions. Essentially, the Maurer-Cartan equation is the condition that the form in this. So, sorry, let me go back. Onischik has a very general theory of non-abelian cohomology, which includes Grothendieck's, but it also includes a non-abelian Dolbeault cohomology as a particular resolution. So this non-abelian Dolbeault cohomology theory, the Maurer-Cartan equation, which we have which appears in the previous slide, is the condition that a 4 be closed. This the condition that two forms are related by this action is the condition that they lie on the same cohomology class. So we can recover we can recover the result of Onischik from the previous two results. Now let us finally relate holomorphic structures with connections, which is what we need to write down the equations. Let me fix G, a complex connected reductive group, X, a complex n-dimensional manifold, a smooth G bundle, a maximal complex group subgroup of G, a smooth K reduction, and well, just a little reminder, a connection in EK. This, of course, works as well for any smooth bundle, but not to clutter the notation I stated for EK. A connection is a smooth K equivariant splitting of this short exact sequence, and it can also be identified with a K equivariant one form B on K with values in the Lie algebra of K. Basically, once you have a splitting, this is given by projecting this tangent bundle onto the vertical part. We denote by AK the space of connections, and again, this was part of Brian's course last week, but we have a one-to-one correspondence between holomorphic structures in EG and connections in EK whose whose curvature has vanishing 0-2 part. And this is known as, this was put by Singer, is a generalization of the Chern correspondence. So we refer to it as the Chern-Singer correspondence. Now let me fix a parabolic subgroup of G and assume that EG is a smooth G extension of the structure group of a certain P bundle EP. And this is the section associated to extension of the reduction, however you want to look at it. And we have this definitional lemma, which is definition/lemma, that there exists an operator on the space of sections induced by the connection B, such that this B and psi solving this equation is equivalent to psi being holomorphic. So from this lemma, together with the Chern-Singer correspondence, we know that there's a one-to-one correspondence between holomorphic structures in EP and connections in EK, whose curvature has vanishing 0-2 part, and that satisfies this coupled equation. Essentially, we are identifying holomorphic structures in EP with holomorphic structures in EG which have a holomorphic reduction. This is one possible generalization of the Chern-Singer correspondence to holomorphic P bundles, but we can use the characterization of holomorphic structures with an L reduction that I gave before to give yet another generalization of this fact. For example, now let me fix a Levy subgroup of P, a smooth L reduction. I take a maximal compact subgroup of P that is well aligned with K, just like in the course by Gergely-Berti, and a smooth Q reduction. And in this case, we have yet another generalization of the Chern-Singer correspondence, which asserts that there exists a one-to-one correspondence between holomorphic structures here and pairs where A phi, where A is a connection in the Q reduction, phi is a 0-1 form here, and they satisfy this coupled system. So essentially, this is just a consequence of the theorem that I said before about how we can identify holomorphic structures in a bundle with a non-reductive group with a pair, and together with the Chern-Singer correspondence to identify the induced holomorphic structure on the L reduction with a connection. So we get this, and this is the integrability, what corresponds to integrability condition on the holomorphic structure. And let me state that I've stated this for EP, but it works for arbitrary connected linear algebraic group. And moreover, now we have, so to speak, two generalizations of the Chern-Singer correspondence. How can we relate the data that appears in both generalizations? Well, let me denote by tau the C antilinear involution associated to the compact real form K at the Lie algebra level. And iota is the L reduction of EG, which you get by composing the P reduction of EG and the L reduction here. And so the connection upstairs is related to this Chern-Singer pair by this simple formula here, which is the exact analog of this formula for the Chern connection. The only you should bear in mind that the 0-1 form, when restricted to extensions, is equal to this 0-1 form up to a minus sign. So this is why these two minus signs appear. So we now understand holomorphic structures. We now understand how to encode them in terms of connections. So we have what we need to start writing down gauge equations, or equations that generalize these three equations over here. First off, we're going to try to generalize this first equation over here. And the generalization, I will be referring to it as the non-central Hermitian-Yang-Mills equation. So first I need to fix the following data: G, a complex connected reductive group, P, a parabolic subgroup of G, now a compact n-dimensional scalar manifold. Now I do assume that the manifold is scalar and that it has omega scalar form. E.g. a holomorphic G bundle, the smooth holomorphic P reduction of the bundle E.g. And we fix a maximal compact subgroup of P and a corresponding smooth reduction, together with a maximal compact subgroup of P, which is well aligned with K, and a smooth reduction, again, of the P bundle to Q. And finally, we take C, an element in the center of the Lie algebra of Q. And let me remark that, of course, when we have C, C defines a constant element in this space over here, which we can identify with equivariant maps from EQ to Q. So C defines such an equivariant map, this is the constant map. And by equivariance, we can embed this equivariant maps from EQ to Q, to the Lie algebra of Q, inside this maps from EK to the Lie algebra of K. The embedding depends on this side here. So the image of C under this embedding, I will be referring to it as C subscript psi. Now, what are going to be the unknowns in the equation? Well, here in the equation for extensions, it was a Hermitian metric on the bundle E in the middle, but that's equivalent to having the unknown being a connection. So the unknown for me is going to be a connection in a case such that the 0-2 part of the curvature vanishes and satisfying this couple condition with the P reduction. And so the non-central Hermitian-Yang-Mills equations, the general version of these ones over here is just this one. Again, the left-hand side is just the usual Hermitian-Yang-Mills term. And the right-hand side is what I want to write as the right-hand side is this constant, but for the equation to make sense, I must use this embedding. So it's C subscript psi. And this having the constant line in the center instead of in the center of the Lie algebra of K is going to give us some extra freedom, which is the freedom of choosing two different parameters in the case of extensions. Now, the problem we want to address regarding this equation is the existence problem. If I fix a connection satisfying the conditions that I stated before, is there a gauge transformation in the gauge group of EP of the P reduction such that G acting on B is a solution to the non-central Hermitian-Yang-Mills equation? First observations, if you prefer to think of these equations as metric equations instead of gauge equations, you can safely do that. Of course, you must understand that a connection in a principal bundle is a reduction to a maximal compact subgroup. But with this understanding, you can equivalently study the metric problem. These two conditions are invariant under the action of GP of the gauge group of EP, but the equation itself is only invariant under the action of GQ, so the associated unitary gauge group, so to speak. So this motivates the following uniqueness condition. We say that the question above has a unique solution if given any two gauge transformations in GP such that when both act on B, they both yield solutions of the equations, then there exists an element in the unitary gauge group such that G1 and G2 are related. So basically the best uniqueness we can hope for is uniqueness up to GQ action. So this is what we define as having a unique solution. And by chain-based theory, the values of the parameter C are restricted, but they are no longer fixed. So we have free parameters in the equation. Now, let us look at the moment map interpretation. Well, first of all, let me remind you about the usual moment map interpretation of the Hermitian-Yang-Mills equations in the principal bundle setting. So let us consider the space of connections on EK. This has a natural GK action. It is symplectic, with the symplectic form is given by this formula over here, but this strange product, this strange looking product is just a combination of the usual wedge product on the form part with an invariant inner product on the Lie algebra. And these are two elements in the tangent space. It also has a natural complex structure given by this expression once we identify the tangent space at any point with like this. And so we can prove that this triple is an infinite dimensional and Kähler. And so if we restrict to connections whose 0,1 part of the curvature vanishes, which is equivalent to the curvature being of type 1,1, then we have an infinite dimensional Kähler submanifold of this. And as we know from the talks in the previous week, we have this very celebrated theorem of Atiyah and Bott, which was generalized by Donaldson to higher dimension. And this says that the action of GQ on AK11 on the connections with curvature of type 1,1 is Hamiltonian with a moment map given by this expression. Here I'm embedding, this is the Lie algebra of the gauge group, and I'm embedding it inside its dual using a natural pairing, but up to that, this is the usual formula. So let us try to see how we can use that to give a moment map interpretation of this non-central Hermitian-Yang-Mills equation. First, we take the space of these connections with vanishing 0,2 part, which are compatible with reduction psi in this sense. And now, as an immediate corollary of the result of Atiyah-Bott-Donaldson, we get that the moduli space of solutions to the non-central Hermitian-Yang-Mills equation is given by taking the level set under the Atiyah-Bott-Donaldson moment map of this element, intersecting it with the connections that we want to take as unknowns, and we mod out by the action of the unitary gauge group. This is a subset, possibly with singularities of the symplectic reduction, this symplectic infinite dimensional symplectic reduction. And this infinite dimensional symplectic reduction has the interesting or surprising or remarkable feature that it's a reduction in a non-central orbit. Of course, in the usual theory of symplectic reduction, this is nothing special, but at least to my knowledge, this is not so common in the infinite dimensional setting, at least when you're trying to understand gauge equations as a moment map. So this gives a symplectic interpretation of the first equation over here. And moreover, actually, we can even identify this symplectic reduction as the moduli space of solutions to this equation itself if we allow for more general solutions. In the following sense, just for example, to let us, for simplicity, take a look at the equation for extensions. The only thing that we are using for this equation for extensions to make sense of the equation is that this extension at the smooth level splits. So it is, the smooth level is a direct sum E of E1 plus E2. But this equation just makes as much sense if you are looking for solutions which are extensions in this direction or extensions in the opposite direction. So we can, it is conceivable that this equation includes more general solutions to the ones which are induced by holomorphic structures or by a P reduction. So, and if we include such more general solutions, we can identify this with the actual moduli space of these more generalized solutions. For example, like I said, this more general moduli space may include solutions which appear as extensions in one direction or in the other. The way to translate this statement in the general setting is it may include solutions coming from a parabolic or an opposite parabolic subgroup with respect to a fixed Levy subgroup. And in some instances, it may include even more exotic solutions. This is so this, whether it includes more exotic solutions or in which situations, this is something that we are currently working on. Now, on to the second equation. Before introducing it, we need to make a brief digression to study the Kähler structures in this flag variety. So we fix G a connected complex reductive Lie group, P a parabolic subgroup of G, and we assume that it's standard, that it is a standard parabolic subgroup associated to a choice of simple roots, the semi-simple part. And we assume also that we have fixed a Cartan subalgebra and so on. And also K denotes a maximal compact subgroup, and Q a maximal compact subgroup of P this time, which is well aligned with K. And G mod P is diffeomorphic to K mod Q, so G mod P admits a natural transitive K action. And we have this well-known proposition that there exists a bijection between K invariant Kähler structures here and these combinations of the root vectors associated to the simple roots where this tau alpha here must be positive for the bijection to hold. The Kähler forms that appear in this proposition correspond to the Kirillov constant Souriau symplectic forms in an orbit of the coadjoint action induced by and the relation is induced by the killing form on the semi-simple part. And because these symplectic forms are very well understood, we can immediately say that the K action on this Kähler manifold is Hamiltonian, and the moment map is given by this expression. Okay, so now on to the second equation. We fix the following data: G, P, K, and Q as in the previous slide, and we fix the Kähler structure and associated moment map again as in the previous slide. X omega is a compact n-dimensional Kähler manifold. We fix again a holomorphic G bundle and a smooth reduction of the structure group to K. And this time an element in the center of the Lie algebra of K, which I call C hat. And the unknowns this time are going to be a connection in EK such that the 0-2 part of the curvature vanishes, and a holomorphic P reduction of EG, or a smooth reduction which satisfies this couple condition. So we can write down, in this case, this following equation, which we term the Hermitian-Yang-Mills-Higgs equation, which is the analog of this equation over here. It's not the analog, it's the generalization of this equation. And again, a remarkable feature is this is a particular instance of a very general equation for pairs introduced by Ignasi Mundetti Riera in the year 2000. Again, we want to address the existence problem, so for which pair satisfying the conditions above is there a gauge transformation now in the gauge group of EG such that G acting on the pair is a solution to the Hermitian-Yang-Mills-Higgs equation. Again, this is equivalent to a metric problem if you prefer it to state it in such a manner. These two conditions are invariant under the action of the full complex gauge group, but the equation itself is only JK invariant, so invariant under the unitary gauge group. And this motivates the following uniqueness condition, which is the analog of the previous one. We say that the solution is unique if any two gauge transformations which yield a solution lie in the same orbit of the unitary gauge group. And by Cherny theory, the value of the parameter C hat this time is fixed, which appears to be in contrast to the previous equation, but let me remind you that at the very beginning we have fixed a hidden parameter here, the Kähler form on the flag variety. And also, Ignasi Mundetti Riera in 2000 gives a symplectic interpretation of the equations. It's a very natural symplectic interpretation, but in the interest of time, since this is better known, I'll skip this symplectic interpretation. And now, let us prove or discuss what is the relation with the previous equation. So, given a constant Lie algebra of Q, we can always write it down in this way, where C hat is an element in the center of the Lie algebra of K, and this is if we assume that the parabolic group is standard, this is a combination of root vectors. So we made this, if we made this assumption about the positivity, which we had to make to relate it to Kähler structures, under the inclusion map that I fixed above, this part here maps to the minus moment map, fiber-wise extension of the moment map evaluated at the reduction of structure group. And now, if I fix a pair with these two conditions, we have the following proposition, which asserts that the existence of a solution to the first equation, in the sense that I've introduced above, is equivalent to the existence of a solution to the second equation. And moreover, we have a unique solution for the existence problem in the first one, if and only if we have a unique solution for the second one. So unique up to the action of the corresponding unitary gauge groups, which are different in these two cases. So the upshot is we have existence and uniqueness for are equivalent for both equations. So this equation, their generalizations are also equivalent. And now onto the final equation. We want to generalize this system now. So the data, parabolic subgroup of a complex connected reductive group, a compact and dimensional Kähler manifold. I fix EP to be a holomorphic over X, a holomorphic P bundle. L, a choice of Levy subgroup of P, and U denotes the unipotent radical. And K is a maximal compact subgroup of G. And I fix again Q, a well-aligned maximal compact subgroup of P and L. This choice can always be made. And I take the smooth reductions and I denote by tau the antilinear involution associated to the compact real form K on G. And C, let us fix an element in the center of the Lie algebra of Q. So very similar data to the first equation and the second one. But now the unknowns are going to be a connection on the Q reduction with vanishing 0-2 part of the curvature, and a 0-1 part, or a 0-1 form, on X with values in this associated vector bundle such that A and Q satisfy this coupled Maurer-Cartan equation. So let me remind you, these two data are in one-to-one correspondence with holomorphic structures in EP. So I take these two as the unknowns of my equation. And the coupled Hermitian-Yang-Mills-Hodge equations, which is the name that we give to the generalization of this equation over here, is given by this system. As you can see, this is there are the usual Hermitian-Yang-Mills terms. This is the harmonicity condition coming from Hodge theory. And these are the coupling terms depending on this bracket. And actually, if the unipotent radical is abelian, we can prove that this term here disappears, this coupling term in the second equation. So the second equation is just harmonicity in the sense of Hodge theory. And so that's the reason for the name Hodge in the equation. So in some sense, we can interpret this as a coupling between the harmonicity condition in Hodge theory and the Hermitian-Yang-Mills equation. The existence problem, once again, for which pairs, such as above, is there a pair J hat F lying here, which let me remind you that it's just a gauge group of the P bundle, such that when this acts on the pair, this yields a solution to the equation. So this is the existence problems that we want to study. Again, these conditions on the A and phi are invariant under the action of the gauge group, but the equations themselves are only invariant under the corresponding unitary gauge group. So this motivates the following, again, uniqueness condition, which, well, essentially is a solution is unique if it is unique up to the action of JQ, which translates to these two conditions under this identification of the gauge group. And by Chernobyl theory, once again, the value of the parameter for which there may exist solutions is restricted, but it's not fixed. So once again, in the equation, we have three parameters. And let us now fix the following data. We fix a G extension of the structure group of EP. Psi denotes the associated smooth section. AK is the smooth K reduction of EG. And now we let B psi be the data that is associated to the holomorphic structure in EP by the first generalization of the Chern-Singer correspondence, and A phi be the other data in the second generalization, so what I've been calling the Chern-Singer pair. And these two elements, we assume that they both correspond to the same holomorphic structure under the bijections I stated before. And in this context, we can prove once again that the following statements are equivalent. The fact that there's a solution lying in the complex gauge orbit of this pair of the non-central Hermitian-Yang-Mills equation is equivalent to the existence of a solution to this equation here, to this coupled system, in the same sense. And moreover, the solution to 1 is unique if and only if the solution to 2 is unique. So just like in the case of extensions, we have proved that we have these three equations. These three equations are different, but they are all equivalent. And moreover, we have a moment map interpretation of this equation. We have a moment map interpretation of this equation. So we should have a moment map interpretation of this equation. But this is where trouble begins, because well, let me remind you that the gauge group is written in this form. And an important part in the Atiyah-Bott-Donaldson moment map is that the unitary gauge group, the full gauge group, sorry, is the complexification of the unitary gauge group. So the unitary gauge group here is GQ. And this is a problem because the complexification of GQ is not GP, it's GL. So one thing we could do is we could try to just give a symplectic interpretation of this action of this subgroup, which was actually done by Steve, Bradlow, and Oscar in their original paper. But if we want to include somehow this extra part, this looks absolutely hopeless. Or it would have looked absolutely hopeless 2 days ago, because if you remember in the session of the course by Gergerly-Berthy yesterday, he introduced a more flexible notion of moment map, which is particularly well suited to deal with actions of non-reductive groups. And this gauge group looks eerily similar to what a non-reductive infinite dimensional gauge group should look like. So let us try, not with the usual moment map condition, but with this generalized moment map. In the original paper, they call it omega moment maps. That's why I call them like that here. So let me fix the space of these Chern-Singer pairs. And this space is in bijection with this other space, which I introduced before. And the important part is that since this is a Kähler submanifold of this can be identified with an infinite dimensional Kähler submanifold of this infinite dimensional Kähler manifold here. Well, this is a technical part that Kirwan and Berthy used in their paper. Basically, it's more convenient in this setting instead of fixing one maximal compact group and a K-invariant Kähler form to fix a whole orbit's worth of such pairs. So this is what I mean by GG equivariant Kähler structure. That is not very important. It's determined by the usual structure. And this generalized or equivariant Kähler structure induces a similar Kähler structure or equivariant Kähler structure in this space over here. So the theorem now is that the holomorphic action of the gauge group on the space of these Chern-Singer pairs is Hamiltonian, not in the usual sense, but in the sense that we were introduced to yesterday, which means that there is a non-reductive moment map or an omega moment map given by this expression here. So essentially, the left-hand side of our equations are an omega moment map. And this is once you realize that the natural notion is not of moment maps, but omega moment maps, this is just a natural consequence of this relation that we introduced before. So the curvature of B and the curvature of A and exotherms on phi are related by this. So if we compute them and project the usual Atiyah-Bott moment map, we get this expression here, which gives a omega moment map interpretation of our equation. So we have a moment map interpretation of the equations, in particular of the generalization of the harmonicity condition. And also this gives a natural non-reductive analog or generalization of the moment map of Atiyah-Bott-Donaldson in this situation. So we've introduced the equations, we've seen that they are equivalent. They have different moment map interpretations. And now the next question is, what about the stability? Well, let me fix G, a connected reductive Lie group on a connected compact n-dimensional Kähler manifold, and e.g. a holomorphic G bundle, and a meromorphic P reduction sigma on EG. P is a parabolic subgroup, is a meromorphic section of this associated bundle. So what this means for us is that there exists a maximal open subset, X naught, with codimension of the singularity set at least 2, such that the reduction is defined over this big open set, like Thomas called them yesterday. And the fact that we have to take meromorphic reductions is exactly the same reason. It happens for the same reason as in the usual classical case. To check for slope stability, it's not enough to check holomorphic subbundles, you have to check coherent subshifts. So this is the analog of that in the principal bundle setting. Now, given an antidominant character of the Lie algebra, there exists a positive integer such that this character exponentiates to a character in the group. And the same definition that Thomas gave us yesterday works for the degree here. given a parabolic subgroup of G, a meromorphic p-reduction, and chi an antidominant character, we define the degree in such a manner. So don't be misled by the 1 over n. It just appears because the character that I took initially was not a character in the group, but if I had taken a character in the group, this would have not appeared. And alternatively, we can compute the degree using the curvature of an induced connection in the style of Chen-Wei theory. And now, let me state some conditions of stability, semi-stability, and polystability. Let psi be a holomorphic p-reduction of EG, and I fix a constant in the center of the Lie algebra of Q. And the holomorphic bundle, EG, we say that it is psi C stable, or respectively psi C semi-stable, if for every parabolic subgroup P prime of G such that P prime belongs to P, and every meromorphic reduction and every antidominant character in the Lie algebra of P prime, we have this numerical condition. Respectively, this is strict inequality, so non-strict inequality. And we say that it is polystable, psi C polystable if it's semi-stable, and for all P prime parabolic subgroups of G such that P prime belongs to P, all P prime meromorphic reductions and all strictly antidominant characters such that we have this equality, the meromorphic P reduction is induced by a holomorphic reduction of structure group to a Leveson group over all of the space. So some comments. In the talk by Thomas yesterday, this was not a greater than, it was a lower than, but this is because I've taken antidominant characters instead of dominant characters, so there's no problem with that. And moreover, if I take P to be equivalent to G, so my group is no longer non-reductive, these conditions are just equivalent to the stability conditions for principal bundle. So this is a direct generalization of these conditions. Well, moreover, Luke and Telemann in a paper in 2006 proposed some equivalent stability conditions for a pair, EG and psi. And moreover, the stability conditions can be restated in terms of the P bundle EP directly. So if you look at the previous slide, actually the definition of degree works also in the case where the bundle has structure group P. So we could have stated the same stability conditions directly in terms of the P bundle. In that case, it doesn't make sense to mention the reduction explicitly. So I will refer to them as C stability and C polystability, semi-stability, and so on. But you can state them directly in terms of this data. Now, Luke and Telemann in 2006 prove a Hitchin-Kobayashi correspondence for pairs, actually for very general pairs, but the part which we are interested in is that our pairs belong to the sort of pairs that they study. And the Hermitian-Young-Mills Higgs equation, which is the same equation which was introduced by Ignacio Mundetti-Riera. Actually, Mundetti-Riera gives part of this Hitchin-Kobayashi correspondence in his original paper as well. And we have a saying in Spanish. We say that lo prometido es deuda. So since in the title of the talk, I mentioned the Hitchin-Kobayashi correspondence, what is promised, a promise is a debt. So here is the fulfillment. We have a Hitchin-Kobayashi correspondence in this situation as well. First, let me state it for this first equation, what in general I've been calling the non-central Hermitian-Young-Mills equation. So let B a connection such that these two couple conditions are fulfilled. Then there exists a gauge transformation in the gauge group of the P reduction such that G acting on B is a solution to the equation if and only if EG is polystable in the sense that I introduced in the previous slide. And moreover, if the bundle is not only polystable in this sense, but also stable, then the solution is unique. This result follows from the following. It follows from the Hitchin-Kobayashi correspondence of Luke, Telemann, and Mundetti-Riera. And it follows also from the equivalence of the stability conditions that we've introduced to the ones that they introduced, and of the equivalence between the equations. And by the equivalence between the three equations and the previous data, we have yet another Hitchin-Kobayashi correspondence, an equivalent one, for the other version of the equations, the version that is a coupled system. And so in this case, let E phi it be a Schoensinger pair. So there exists a pair lying here, which is isomorphic to this, such that this gauge transformation acting on this pair is a solution to the equation if and only if the bundle is polystable, and moreover, in the sense of the previous slide, and moreover, if the bundle is stable, then the solution is unique. So we do have a Hitchin-Kobayashi correspondence as a consequence of the previous of the equivalence between the previous equations and the some Hitchin-Kobayashi correspondence in the literature. So, as some final comments, a lot of what I've said so far works, comments for different communities, so to speak. For people who are interested in non-scalar geometry, actually a lot of what I've been saying works when the base manifold is non-scalar. So if anyone wants me to elaborate on that, on the questions, I'll be happy to tell which parts can be generalized straightforwardly and which parts are more subtle. And more importantly, there is a relation between all this program with some of the foundational problems, or let's say some of the problems that inspired, to the best of my knowledge, the theory of non-reductive GIT. Because one such problem, to the best of my understanding, is to understand the moduli space of unstable vector bundles of a fixed Harder-Narasimhan type. Well, if we identify this unstable vector bundle with the filtration that is given by the Harder-Narasimhan filtration, then actually what we have is a moduli problem for filtrations, or in particular if the filtrations just has one step, is a moduli problem for extensions. So this problem has been dealt with, or parts of the particular instances of these problems have been dealt with the methods of non-reductive GIT, for example, in a paper by Joshua Jackson in 2021, if I'm not mistaken. And our approach, our get theoretical approach, appears to be well suited to give an alternative approach to that moduli problem. In particular, I don't know if I've emphasized this enough, this is not just one stability set of stability conditions. These are a family of stability conditions depending on parameters, because this C here actually hides some free parameters. And and it appears that, for example, in the work of Joshua Jackson, he introduces some stability conditions to deal with a particular instance of this problem. And it appears that that stability condition is compatible with ours, at least in some regimes of the parameters. So we are hopeful that there might be a strong connection between those sort of results and the approach that we have taken here. And otherwise, I just thank you all for your attention.
Okay, any questions?
Yes? No.
Hello? Okay. So I have some really basic questions. So this EG is G bundle. G is the reductive group.
Yeah.
And this stability condition, so we're assuming that for this to be interesting, I guess this has to be like an unstable, typically unstable G bundle.
No. For our setting, these are the stability conditions, and this is what we define as stable, and we actually need that to prove the correspondences. However, we can relate that to the problem of understanding moduli of unstable vector bundle. So in a sense, what we are given is a tentative family of stability conditions that work for unstable bundles, so to speak.
So the starting point is EG with reduction of structural group to P.
Yeah.
So is the following true, that if if this P bundle comes from a bundle for the Levy quotient, then it cannot be semi-stable. Is that true or false?
Well, if it comes from a Levy quotient, then it's this reduces to the well, at the level of equations, if it comes from such an L reduction, what this means is that the phi's are all gone, they're vanishing. So essentially, I'm doing a little bit of upside down, but if you look at the equations, that the stability has to be the stability for the Levy. So since we know that there's a correspondence, the stability here is just the stability for the Levy in that case.
Okay. Okay.
So, but you can prove that from the stability conditions as well. But in my mind, it's clearer from the equations.
Thank you.
Can make a comment on that. In this particular case of extensions, and that applies to the general situation, as Diego mentioned, there are parameters of stability. In this particular case, there is a real number. And so there is one particular value, 0, for which the stability of the extension coincides with the stability of the bundle E there, while there is another stream where the stability coincides with the semi-stability of the two bundles E1 and E2. So there is, because of this freedom, there is a relation, the stability of the Levy, but depends on which value of the parameter you are in. And this applies in the general setup.
Yeah, and also to elaborate on that, even if there is not that reduction, a holomorphic reduction to the Levy, it might be the case that in some regime of the parameters, the stability conditions are equivalent. This actually happens for extensions. There's a very particular regime of the parameter that in extensions where the stability coincides, the stability of, in this generalized sense, coincides with the stability of E1 and E2, which correspond to the Levy. So yeah, that's also something that can happen in a particular regime of the parameters.
Gurley, you have a question.
Hello? Okay. So, so you mentioned that now you have this Bowman map interpretation for the equations for parabolic gauge. Can you? Yeah. So you mentioned that you have this Bowman map interpretation of the in the parabolic gauge case. Is it so? Is it still true that if you take, can you identify the solutions as sort of quotient of the for some level set for this non-reductive moment map?
Sorry, I didn't hear the last part.
So does this general principle goes through in this case that if you have this non-reductive setup and you just identify the equations with the non-reductive moment map, then the zero level set modulo the Q, which is just the maximum compact in this case for non-reductive gauge group, that gives you the parametrization of the solutions or some subset in that. In other words, you had this term like two solutions are equivalent if and only if there is a compact group action sending on the level set, sending one into the other. Does it go through for this non-reductive moment map situation?
That's a very good question, and it's very subtle. So the problem, let me go back a little bit. Okay, so here are the equations. As I understand, for that to hold, we would need that the solution to phi here in the second equation to be unique, which happens, for example, if the unipotent radical is abelian, this is just a harmonicity condition. So we have a unique solution. If there's a solution, there's a unique phi that satisfies it. So in that sense, in that case, for example, that would be true. However, we do not know in the general case the uniqueness properties of this second equation alone. So we cannot. It's a reasonable thing to expect that, but we cannot say for sure until we understand better this second equation.
Yep. One more question over there.
Yeah, also somewhat basic question. So in a special case for like say extensions, so you also have this Hitchin-Kobayashi correspondence. For the stability side, Is there some sort of interpretation of the stability that you stated in terms of like some sort of slope stability?
Yeah, it's actually, I did not mention it, but it's actually a slope stability on the nose. So for the extension, what you take is you define a slope function depending on a certain parameter. So let me call the extension E. And you define the slope as the slope of the bundle in the middle minus alpha times the rank of E2 . So this is your slope function for an extension, and it depends on a parameter. And essentially, the stability conditions are, so you test the coherent extensions given by coherent subsheaves. You compute this alpha slope of such a coherent subextension, and then you have the same condition, the usual slope stability condition. The subobjects must have strictly lower or equal alpha slope, and the polystability is just what you would expect, that it splits as a direct sum. So yeah, in the case of extensions and even filtrations, which are, I didn't mention it, but there's also the case of extensions is already known by work of Luis Albert Consul and Oscar as well, and the same story goes through, yeah.
Okay, last question before I break.
One side of this seems to only depend on the parabolic
Hmm.
group P. So I guess you've thought about the case in which you replace it by any non-reductive group?
Yes, but that's a very good question. So in this work, we're not dealing with this, but we know some things about the general situation. For example, the equivalence of the equations in the general situation is false. They are no longer equivalent.
Maybe you need to grade it in the sense we just learned.
It's not clear. It's not clear to us at this point if an additional condition allows us to get, for example, this third equation here, which corresponds to the equation introduced by Ignasi Mundetti Riera. It's difficult to make sense of that whenever P is not a parabolic subgroup, because the way that we've introduced it, it depends very much on the precise classification of K-invariant Kähler structures. So it might be the case that it works for some other groups, but maybe we don't have such a good knowledge of the Kähler structures. So whenever the structure group is non-parabolic, the equivalence between the equations it ceases to exist. But the equations themselves make sense for general. For example, if you take the system here, the scalpel system. I've not said it, but in this scalpel system, if you try to write down the equations for the additive group, and you take as G GLN2, the additive group embeds as upper triangular matrices with 1, 1 on the diagonal. These equations is just the harmonicity condition in Hodge theory. So you can make sense of the equations. And also, so the harmonicity conditions in Hodge theory are an omega moment map in some sense. So it makes sense to ask the question, but the way that we approach it is through the equivalence of the equations, and since that doesn't hold, we can say very little in general.
Okay, well, given us lots to think about. Thank the speaker again.